function, it raises an alarm. And of course, it's bundled with some programming languages. It doesn't have a high runtime penalty or memory penalty. With granular character information, we may use it both in development and in production. We have fewer false positives because we have more information about the string's composition. We also have more precision and per character information. And we can model vulnerabilities based on this granular information, allowing syntactical checks over strings. Of course, we are dealing with an increase of penalty in memory and runtime, which we'll discuss later. So now we made a brief description about the threats, a technique to identify or to track information inside a web application, which we will use it for designing our solution. And now we will locate our solution in a very basic schema of a web applications architecture. Imagine if a person reviews all the data entering a web application or leaving the web server, deciding whether if the data is dangerous or not for its output or for entering the web application. And when the data enters the web application, he marks it as dangerous because it's being provided by an untrusted source. We can also locate this person on the three bullets which are painted, and this person can also watch if the data being passed to a backend server, for example, a database server, it's dangerous for its execution. And he also could mark data incoming from the database server. For example, if stored HTML code is being retrieved from the database, he could see if this code could result in a cross-site scripting attack, for example. So he would know if this data is dangerous for the application to be used by the application. So GRASP is located in these three layers. The first layer, which is between the web server and the outside world, marks all incoming data from untrusted sources and prevents harmful data from being output to the outside world. And there also privacy policies are enforced, which are defined over the data. The second layer, which is inside the execution environment, tracks all the information which was marked at the beginning, at the first layer, and it tracks all the flow of the information inside the web application. The third layer, which is located between the web server and the backend servers, checks outgoing data for attacks. It also checks for incoming attacks, which may be, as I said, dangerously formed HTML code. And it also enforces privacy policies and marks all incoming data from databases as untrusted. So the design principles we followed was we would modify for each language the way any web application receives, handles, and outputs data in order to prevent injection attacks. The security information is tracked inside the web application's execution environment. As I said, we use a technique of character granularity information. And we will classify data operations and functions into three groups. The first one are sensitive sources, which are the functions or the places where data is entered to the web application and should be considered untrusted because they form attack vectors to our web application. We also define sensitive sinks, which are functions or modules where we have to check the data we are supplying them in order to execute some operations. And data manipulation operations are those in which we must handle this security data and propagate the security information of the data inside the web application. So each of these operations must be modified to be security aware. So as an architectural description, for each programming language, we modified its execution environment, augmenting it to add additional information about security over the strings. And we can identify possible sensitive sources at get post variables, for example, environment variables such as HTTP headers, cookies or session variables, and incoming database data. Some possible sensitive things which we have to be aware of are queries sent to the databases, of course, data received from a database which will then be output to a user, for example, to protect cross-encryption attacks. All these attack vectors, which can be controlled by an attacker, must mark the information as dangerous because we later can use it to perform a sensitive sync operation. Of course, security data is propagated among data manipulation operations. So how do we protect? Well, we decided to implement the protection over sensitive things with finite state machines, which was a technique that resulted for us. We may choose another technique. So having this granular information about strings, we could analyze them with these finite state machines and state whether a string is would be dangerous for our application to execute it. The important thing about this is that this protection is deterministic for each family of vulnerabilities. For example, we design finite state machines for protecting SQL injection attacks, another finite state machine for protecting against cross-encrypting attacks. So inside a web server, the protection against the attacks is the same for all the web applications. And we don't have to modify the web application for that purpose. Here we have an example of a finite state machine. I don't know if you can read something. Here we have a query with an attack, a simple attack. So we start here at this state, and each time a character is read, we follow into a transition. For example, every time we take a character with mark harmless, we stay in this state because there is no arrow for going out from this state without when analyzing a character with harmless mark. Maybe we should add here a loop arrow. But when we reach this, But when we reach this quote here with dangerous mark, the machine transitions to this state, which is a quote with this here. Well, I can't find it right now. Oops. Well, it transitions to another state. Here, in the first quote, we have a not marked quote, so the transition is made to this state with a quote without a mark, and then we have another quote with dangerous mark over it. So when it reaches a dangerous quote with a mark that closes a safe quote, it reaches the attack state. Well, here we have different kinds of identifications. We base this finite state machine on MySQL's lexical analyzer, so it protects against SQL injection this way. So, which are the security features of our system? Injection attacks are detected and can be prevented or blocked. Every web application which is in the web server we are installing the protection system is protected immediately. A finished state machine checks for cross-language boundaries, which are these places where SQL, for example, SQL queries are made inside PHP applications or shell command injections. All attacks are logged, and we can define if we want to block them or not. And we don't need source code modification or ad hoc checks. In privacy meanings, we can define privacy policies over data and describe how a system should manage that data. A privacy officer could define the privacy policies over the data, and the sensitive sources tag information accordingly to these privacy policies. Sensitive sinks enhance privacy and make sure that those policies are enhanced. Data manipulation operations also propagate these tags, these privacy tags. And the data inside the execution environment always have a privacy tags associated. For example, let's say a database stores credit card numbers from users. So this data should never be sent out to users, or for example, we could define a policy that states data from this column should never be printed, or data from this column should only be printed to its owner. That's an example of a privacy policy. So when a database, when a web application sends data to the end user, this policy must be enforced in order not to fall into a privacy violation. So, as a summary, these ideas can be directly implemented for PHP. We developed a prototype, which we have seen a demo, which is a modification of the PHP interpreter. We choose PHP because we had the source code available, and there are lots of PHP vulnerabilities reported each day. So we distribute this as a patch for the interpreter. The installation requirements are the same as the installation for a regular PHP interpreter. We don't need special tuning or training, and we don't have to modify the source code of the web applications that are being protected. So now we'll talk a little bit about the prototype itself. We'll discuss covered functionalities and implementation details. We'll go deeper inside PHP internals, not a lot, and make an architecture description and enumerate the modifications we made. So this prototype is implemented for the latest version of PHP, which is 5.23. But we've been working on this technique since PHP 4. It implements all sensitive sources, so it marks all incoming data from get, post, and cookies variables. We have only implemented one sync protection, which is SQL injection for MySQL databases. The string manipulation operations were modified to propagate marks, except regex. We couldn't make it for this talk. We have implemented an optimization for the marks, so we don't have double space while storing marks over strings. For example, if we have a whole string marked as dangerous, we only store a small amount of data